Download this code from codegive.com, link in the description below. OK, let's dive into the depths of debugging PSA, PlayStation architecture, null access crashes, especially in the context of beta branch errors. This is a complex topic, requiring a good understanding of memory management, pointers, debugging tools, and the specific architecture you're working on, PS4, PS5, or even older consoles. This tutorial will cover 1. Understanding null access crashes *, what they are, why they happen, and common symptoms. 2. PlayStation architecture considerations * specific aspects of the PS4/PS5 architecture that can influence these crashes. 3. Beta branch specifics * how beta branches can exacerbate null access issues. 4. Debugging tools and techniques * a comprehensive guide using GDB and other tools. 5. Code examples * demonstrating common pitfalls and mitigation strategies. 6. Prevention best practices * how to design your code to avoid null access crashes. 7. Advanced topics * using memory analysis tools and advanced debugging scenarios. 1. Understanding null access crashes. A null access crash, also known as a null pointer dereference, happens when your program tries to read from or write to memory at address 0x0, or sometimes near it, resulting in a similar crash. In most operating systems, including PlayStation's Orbis OS, PS4, and possibly a modified version on PS5, address 0x0 is reserved and protected. Accessing it is considered a severe error and will trigger a crash. Why do they happen? Uninitialized pointers * you declare a pointer but forget to initialize it with a valid memory address. If you try to use the pointer before assigning it a value, it will likely contain a null address, or a random, invalid one, but 0x0 is common. Deleted / freed memory * you deallocate memory using free, in C/C++, or another memory management mechanism. The pointer itself still exists, but the memory it pointed to is no longer valid. If you try to access the pointer afterward, a dangling pointer, it's highly probable that it will cause a crash. Logical errors * a complex chain of operations leads to a function returning null or null in C, unexpectedly, and the caller doesn't check for it before trying to use the returned pointer. Concurrency issues * in multi-threaded code, one thread might free memory that another thread is still using, resulting in a null access crash when the second thread tries to use the dangling pointer. Data corruption * memory corruption can overwrite a valid pointer with 0x0 or a value close to it. This can be very difficult to debug because the root cause of the corruption might be far removed from the point of the crash. External library bugs * a bug in a third-party library you're using might be returning null pointers or causing other memory management issues. Compiler optimizations * aggressive compiler optimizations can sometimes expose null pointer dereference earlier, especially when dealing with undefined behavior. While the code was already buggy, the optimizations might make the crash more apparent, or move it to a different line. Common symptoms * crash reports * the PlayStation development tools, example the SDK's debugging suite, will generate crash reports. These reports typically include exception type * usually something like access violation or memory access error. Faulting address * 0x0 or a value very close to it. Stack trace * a list of function calls leading up to the crash. This is crucial for debugging. Register dump * the values of the CPU registers at the time of the crash. These can be useful for advanced debugging. Asterisk debugger stops asterisk when running the game in a debugger, the debugger will halt execution when the crash occurs. This gives you the opportunity to inspect memory, registers, and the call stack. Asterisk game freeze / hang asterisk the game might freeze or hang without a crash report. This can happen if the error handling is poor or if the OS is struggling to recover from the memory access violation. Asterisk visual artifacts asterisk in some cases, especially if the null access is related to rendering code, you might see visual artifacts, example corrupted textures, missing models, before the crash. 2. PlayStation architecture considerations. The specific hardware and software environment of the PS4 or PS5 can influence null access crashes in a few ways. Asterisk memory management asterisk PlayStation consoles use a custom operating system with their own memory management routines. It's important to understand the API calls for allocating and deallocating memory within the PlayStation SDK. Using standard C/C++ memory allocation functions, malloc, free, new, delete, might not always be optimal or fully compatible with the PlayStation's memory manager. Consult the SDK documentation for preferred memory management techniques. For example, they might have specific allocators tailored for different types of memory, example GPU memory. Asterisk address space layout asterisk understanding the address space layout can help you identify invalid memory regions. Know where your code, data, and heap are located in memory. This can make it easier to spot a pointer that's pointing to an obviously incorrect address. Asterisk threading model asterisk PlayStation consoles are highly multi-threaded. Concurrency issues are a common source of null access crashes. Be especially careful with shared data structures and ensure proper synchronization mechanisms, mutexes, semaphores, atomic operations, are in place. The SDK likely provides its own threading APIs that you should prefer over standard C++ threads. Asterisk graphics API asterisk the graphics API, example PSSL or a custom graphics API, might have specific requirements for memory management. For example, you might need to allocate memory for textures or vertex buffers using specific functions or allocators. Failure to follow these requirements can lead to crashes. Asterisk error handling asterisk the PlayStation SDK typically provides error handling mechanisms that you should use to check for errors from API calls. These error codes can provide valuable information about why a function failed and help you identify potential null pointer issues. Asterisk ASAN asterisk address sanitizer, ASAN, is a valuable tool, if available in your tool chain for your target platform. ASAN helps detect memory corruption, use after free, and null pointer dereference. It's often part of compiler tool chains, like Clang. 3. Beta branch specifics. Beta branches introduce several factors that can increase the likelihood of null access crashes. Asterisk new code asterisk beta branches typically contain new code that hasn't been thoroughly tested. This new code is more likely to contain bugs, including null pointer dereference. Asterisk refactoring asterisk beta branches might involve significant refactoring of existing code. Refactoring can introduce subtle bugs that are difficult to detect. Pay special attention to changes in memory management and pointer usage. Asterisk feature flags asterisk beta branches often use feature flags to enable or disable new features. The interaction between different features can be complex, and bugs can arise when certain combinations of features are enabled. Make sure you understand how feature flags affect memory management and pointer usage. Asterisk data incompatibility asterisk changes to data structures in the beta branch might not be compatible with saved data or other data generated by older versions of the game. This can lead to null access crashes when the game tries to load or process incompatible data. Stress testing. Beta branches are often used for stress testing, which can expose concurrency issues and other bugs that are difficult to reproduce under normal conditions. Incomplete implementations. Beta branches may contain incomplete implementations of features, which can lead to null pointer difference if the code attempts to use functionality that is not yet fully implemented. Compiler/linker differences. The tool chain used to build the beta branch might be different from the tool chain used to build the main branch. Compiler or linker changes can sometimes expose hidden bugs or introduce new ones. 4. Debugging tools and techniques. Debugging null access crashes on PlayStation requires a combination of tools and techniques. PlayStation SDK Debugger, GDB. The PlayStation SDK usually includes a customized version of GDB, GNU Debugger. GDB is a powerful command line debugger that allows you to connect to a running game, attach the debugger to a game running on the console, set breakpoints, pause execution at specific lines of code or when certain conditions are met, step through code, execute code line by line to observe the program's behavior, inspect variables, examine the values of variables, including pointers, view the call stack, see the sequence of function calls that led to the current point of execution, examine memory, view the contents of memory at specific addresses, disassemble code, view the assembly code generated by the compiler. This can be helpful for understanding low-level details of the program's execution. Crash report analysis. Carefully analyze the crash reports generated by the PlayStation SDK. Pay attention to the exception type, faulting address, and stack trace. The stack trace is critical because it tells you exactly where the crash occurred and how the program got there. Logging. Add logging statements to your code to track the values of pointers and other important variables. Use conditional logging, if-def debug, to avoid slowing down the game in release builds. Log pointer values before they are used, and log any conditions that might lead to a pointer becoming null. Avoid excessive logging, as it can impact performance. Memory analysis tools. Some PlayStation SDKs provide memory analysis tools that can help you detect memory leaks, corruption, and other memory-related issues. These tools can be invaluable for tracking down the root cause of null access crashes. ASAN is a powerful option if supported by your tool chain. Static analysis. Use static analysis tools to scan your code for potential null pointer difference and other programming errors. Static analysis can identify potential problems before you even run the game. Tools like CodeWright or PVS Studio are good examples. Code reviews. Have other developers review your code, especially code that deals with memory management or pointer usage. A fresh pair of eyes can often spot errors that you missed. Unit tests. Write unit tests to verify the correctness of your code, especially functions that return pointers. Unit tests can help you catch null pointer difference early in the development process. Debugging techniques. Binary search. If you can reproduce the crash consistently, try using a binary search approach to narrow down the source of the problem. Comment out or disable sections of code until the crash disappears, then gradually re-enable code until the crash reappears. Heap validation. Use heap validation tools to check for memory corruption. Heap corruption can lead to seemingly random crashes, including null access crashes. Watchpoints. Set watchpoints in the debugger to monitor the values of pointers. A watchpoint will trigger a breakpoint when the value of a pointer changes. This can help you track down when a pointer becomes null or invalid. Reverse debugging. Some debuggers support reverse debugging, which allows you to step backward through the execution of the program. This can be extremely useful for understanding how a pointer became null. 5. Code examples. Let's look at some code examples demonstrating common null access pitfalls and how to avoid them. Solution * always initialize pointers. Solution * set the pointer to null after deleting the memory. Solution * always check the return value of functions that can return null pointers. Explanation of multithreading example **** shared _ struct ***. This is a global pointer that is accessed by both threads. Shared _ mutex ***. A mutex is used to protect access to shared _ struct. Without the mutex, there would be a data race, where both threads could try to access shared _ struct at the same time, leading to unpredictable results and potentially a crash. Thread 1 ***. This thread allocates memory for shared _ struct and initializes its value. It uses a lock _ guard to acquire the mutex before accessing shared _ struct, ensuring that only one thread can access it at a time. Thread 2 ***. This thread tries to access the value of shared _ struct. It also uses a lock _ guard to acquire the mutex before accessing shared _ struct. Crucially, it checks if shared _ struct is null before attempting to dereference it. This is important because thread 1 might not have finished initializing shared _ struct yet when thread 2 tries to access it. Main The main function creates and joins the two threads. After the threads have finished, it cleans up the memory allocated for shared _ struct. It also uses a lock _ guard to protect access to shared _ struct during cleanup. 6. Prevention best practices. Initialize pointers. Always initialize pointers when you declare them. If you don't have a valid address to assign, initialize them to null. Check for null before dereferencing. Before accessing the memory pointed to by a pointer, always check to make sure it's not null. Use if ptr equals null or equivalent checks. Use smart pointers. C++ smart pointers, example std unique _ptr, std shared _ptr, can help you manage memory automatically and prevent memory leaks and dangling pointers. They automatically deallocate memory when it's no longer needed. RAII, resource acquisition is initialization. Use RAII to manage resources, including memory. RAII ensures that resources are automatically released when an object goes out of scope. Smart pointers are an example of RAII. Avoid raw pointers where possible. Minimize the use of raw pointers. Prefer using references or smart pointers instead. Follow the rule of 0/3/5. Understand and apply the rule of 0, 3, or 5 in C++ when defining classes that manage resources. This helps prevent memory leaks and double freeze. Use const correctness. Use const to declare variables and functions that should not modify data. This can help prevent accidental modification of pointers and memory. Avoid global variables. Minimize the use of global variables, especially pointers. Global variables can be difficult to manage and can lead to unexpected behavior. Defensive programming. Write your code defensively. Assume that anything that can go wrong, will go wrong. Check for errors and handle them gracefully. Code reviews. Have your code reviewed by other developers to catch potential problems. Unit testing. Write unit tests to verify the correctness of your code. Memory sanitizers. Use memory sanitizers, example asan, to detect memory errors. 7. Advanced topics. Memory analysis tools, Valgrind, Purify, etc. If available on the platform, use memory analysis tools to detect memory leaks, corruption, and use after free errors. These tools can be very helpful for finding the root cause of null access crashes. Custom memory allocators. Consider using custom memory allocators to improve performance and memory management. Custom allocators can be tailored to the specific needs of your game. However, they also add complexity and require careful testing to avoid errors. Debugging optimized code. Debugging optimized code can be challenging. The compiler might reorder or eliminate code, making it difficult to follow the execution flow. Try disabling optimizations or using a less aggressive optimization level during debugging. Hardware breakpoints. Hardware breakpoints can be used to break when a specific memory location is accessed. This can be useful for tracking down memory corruption. Reverse engineering. In extreme cases, you might need to reverse engineer the code to understand how it works and identify the source of the null access crash. This is a time-consuming and difficult process, but it can be necessary when other debugging techniques fail. Tools like IDA Pro or Ghidra can be used for reverse engineering. Reproducible bugs. Try your best to reproduce the bug in a controlled environment. Once you have a reliable reproduction, it will be much easier to debug. Postmortem debugging. If you can't reproduce the crash, try to gather as much information as possible from the crash report and logs. This can help you narrow down the possible causes of the crash. Look for patterns in the crash reports that might give you clues. Example debugging scenario, using GDB conceptually, adapt commands to the PSSDK debugger. Let's say you have a crash report with the following information. Exception access violation. Address 0x0. Stack trace 1 renderer draw model, model. 2 scene render. 3 game update. 4 main loop. 1 start the debugger connect the debugger to the running game on the PlayStation. 2 set a breakpoint set a breakpoint in renderer draw model. 3 run the game let the game run until it hits the breakpoint. 4 inspect the model pointer examine the value of the model pointer. If the pointer is 0x0, you've found the immediate cause of the crash. 5 go up the stack use the up command to move up the call stack to scene render. 6 inspect variables in scene render, examine the variables in scene render, to see how the model pointer is being passed to renderer draw model. Look for any logic that might be causing the pointer to become null. 7 continue stepping up the stack continue moving up the call stack and inspecting variables until you find the point where the model pointer is first assigned a null value or becomes corrupted. 8 use watchpoints if you suspect that a particular variable is being corrupted, set a watchpoint on that variable. The debugger will break whenever the value of model changes. 9 use logging add logging statements to your code to track the values of pointers and other important variables. Important notes for PlayStation development SDK documentation is king the PlayStation SDK documentation is your most important resource. Refer to it frequently for information about memory management, threading, graphics APIs, and other platform-specific details. Target-specific tooling always use the debugging tools and techniques that are provided by the PlayStation SDK. They are specifically designed for the PlayStation architecture. Optimization flags be aware of compiler optimization flags. Aggressive optimizations can sometimes make debugging more difficult. Consider disabling optimizations during development and debugging. Platform differences. Be aware of the differences between the PS4 and PS5 architectures. Code that works on one platform might not work on the other. Test your code thoroughly on both platforms. Debugging null access crashes is a challenging but essential part of game development. By understanding the causes of these crashes, using the right debugging tools and techniques, and following best practices, you can minimize their occurrence and create more stable and reliable games. Remember to always consult the PlayStation SDK documentation for platform-specific information. Good luck.